Hi, welcome to YouWillUnderstandMath.com. This is part 2 of understanding the definition of the limit. In part 1, we evaluated the limit of this function at x equals 1, and we discovered that the limit as x approaches 1 of this function is 2. The objective is to find a more generalized form of this notion, and that's what we plan to do in this video. First of all, notice we zoomed in on a small section of the graph. For now, let's focus on the inputs. The inputs will be in this interval between 0.98 to 1.02, but we are not interested in the input at x equals 1, because if we plug in 1 into our function, we have 0 on the bottom, which gives us an undefined problem. That was the whole reason that we needed to use limits, so that we can avoid that 1 point and still get a lot of information about the outputs. Another way to symbolize that x is in this interval between 0.98 and 1, or between 1 and 1.02 without being exactly 1, we'll be using this inequality notation here. This means that x is between these two values, or x is between these two values. Here's another way to write this, which you will see in our definition of the limit. We can say that x is inside of this open interval, 0.98 to 1, but we'll use union for or, looks like a big U, between 1 and 1.02. If there were equality, then I would have to use square brackets. But in this case, we have open intervals. This means that x is to the left of 1 and greater than 0.98, and this means that x is to the right of 1 and less than 1.02. I'd like to have a more rigorous way of describing this very small interval, and the way that we do that is using symbols which denote a very small number, and we're going to use the distance, okay, away from the value of interest. In our case, we were interested in knowing what this function is approaching as x approaches 1. So our input of interest is 1. Let's call that c. Now, how do I talk about how far away 0.98 is away from 1? Well, this interval, this open interval, begins at 0.98 and ends at 1.02. These values are symmetric around 1. For example, we would move 0.02 units to the left of 1 in order to obtain 0.98, and we would move 0.02 units to the right of 1 in order to obtain 1.02. Well, we've moved 0.02 units in either direction. Well, let's call 0.02 a small number, say delta. This is delta. Let's make delta equal to 0.02. So that way we can talk about this small interval in terms of delta, a small distance away from our input of interest, c equals 1. Well, 0.98 would be 0.02 units to the left of 1. In other words, we could subtract 0.02 from 1 in order to get 0.98. Therefore, we would say that this endpoint, this initial point on our open interval, will be c, which is 1, minus 0.02, which is delta. And the same way, we find that the end of our open interval will be c plus delta, because if you add 0.02 to c, which is 1, you'll get 1.02. Using this information, I can rewrite my interval. Remember, 0.98 can be represented by c minus delta, where c is 1 and delta is 0.02, and c plus delta can replace 1.02. Therefore, everywhere I see 0.98, I'll replace it with c minus delta. Everywhere I see 1, I'll replace it with c, and everywhere I see 1.02, I'll replace it with c plus delta. Our interval will go from 0.98 less than x less than 1 to c minus delta less than x less than c, or 1 less than x less than 1.02 will now be c less than x less than c plus delta. And here's the interval notation as well, using brackets. Taking the same approach with the outputs, now we need to find some symbol that will represent a small distance away from our output of interest. Let's use epsilon. Epsilon. Epsilon will represent a small distance away from this output of interest. Notice we already saw that values are approaching 2. We'll go ahead and fill in 2 here. If L represents the value that the outputs are approaching, then moving, in our case, 0.02 units below L or subtracting 0.02 away from 2, we'll get 1.98. Adding 0.02 to 2, we'll get 2.02. And we did choose epsilon as 0.02. One thing to note is that delta and epsilon are not always the same. They can be different, and in fact, they usually are different. In interval notation, we have this. Outputs, f of x, are between 1.98 and 2.02. Notice we are not evaluating f at 1. When we chose our open interval, excluding c equals 1, we automatically avoided this hole. That's why limits work. Here's the definition for a limit. And before I go through this definition, let me reiterate what it means in general, the intuition behind the limit. Here is a general function, f of x. Notice when we created our intervals, our tiny intervals that we created using delta and epsilon, for example, the interval on top, the open interval from c minus delta to c plus delta, excluding c, we call this the delta interval. We also have an epsilon interval, this interval here from L minus epsilon to L plus epsilon. You can see that here as well. From this endpoint to C, the distance between these two values, C minus delta and C, will be delta. This distance will be delta. Similarly, this distance is delta. So we have one delta here and one delta here together. From n to n, this will be a distance of 2 delta. We've created an interval or distance of twice epsilon on this side. From L to L plus epsilon, the distance is epsilon. From L to L minus epsilon, the distance is epsilon. So we've created a length of 2 epsilon here, which I've captured on the other two sides of this rectangle. Epsilon and delta are very small numbers. So we know that this rectangle is tiny. It's very small, okay? Now, epsilon is always positive because distance is positive, and epsilon represents the distance away from the output of interest. Our goal is to see where the outputs are headed as the inputs are reaching some value C here, okay? So as the x values are approaching C from the left side and or the right side, we want to know where the values are headed, the output values are headed. Well, if all of the outputs are always heading for some value as the inputs are heading for this value C, then that means that this output is the limit. Now, more rigorously, our definition says the same thing. For every epsilon, right, for every distance above and below this output of interest, we should be able to find some delta, some distance to the left and or to the right of this value so that the output of that input will be close to whatever this value is. And if it's always close to this value, then this value is the limit. This is the idea of the limit. Thank you for watching. Please like and or subscribe if you've enjoyed this video.